This video gives a quick introduction to artificial intelligence, AI, in about 10 minutes. We'll cover key terms including artificial intelligence, AI, machine learning, ML, deep learning, DL, unsupervised learning, UL, supervised learning, SL, reinforcement learning, RL, Perceptron, Multilayer Perceptron, MLP, large language models, LLMs, Generative AI, Agentic AI, Transformers. We'll start with a brief history of AI development before diving into these concepts. By the end, you'll have a clear understanding of the core ideas behind AI, without getting lost in the technical details. There are two main approaches in AI, one based on statistics and optimization, SO, the other based on neural networks, NN. The foundations of AI trace back to the 1940s and 1950s. On the SO side, pioneers like Ronald Fisher advanced statistical methods for data analysis, which later became essential in machine learning. In 1947, George Dantzig developed linear programming and the simplex algorithm, laying the groundwork for solving optimization problems. On the NN side, in 1943, Warren McCulloch and Walter Pitts proposed a model of artificial neurons, establishing the foundation of neural networks. In 1950, Alan Turing introduced the Turing test, a framework for evaluating machine intelligence. The term artificial intelligence was formally introduced at the 1956 Dartmouth Conference. The period from the 1950s to the 1970s is often regarded as the first golden era of AI. In SO, Bayesian methods were developed, applying probability theory to inference and decision-making. Hidden Markov models, HMMs, also emerged, finding applications in speech recognition and time series analysis. In NN, Frank Rosenblatt created the Perceptron, a simple neural network capable of supervised learning. Although limited in capability, it became a crucial foundation for later advances in machine learning. The 1970s to 1980s is the AI winter. In 1969, Marvin Minsky and Seymour Papert published Perceptrons, highlighting the limitations of neural networks. Their critique led to diminished interest and funding. Meanwhile, SO methods continued progressing. The expectation maximization, EM, algorithm was developed, and support vector machines, SVMs, were introduced, both of which became powerful tools in machine learning. AI research revived in the 1980s and 1990s, though SO methods remained dominant. Neural networks, still considered niche, gained renewed attention through the popularization of backpropagation in 1986 by researchers including Geoffrey Hinton and David Williams. In the early 2000s, major technology companies like Microsoft heavily invested in AI, focusing primarily on SO techniques. Neural networks remained on the sidelines until the rise of big data and the dramatic growth of computational power, especially through GPS. This convergence of SO and NN led to the emergence of deep learning. Powered by techniques such as stochastic gradient descent, SGD, and backpropagation. At the same time, advances in probabilistic programming, example, frameworks like Pyro and Stan, made it easier to build and infer complex probabilistic models. By the late 2010s, the integration of statistics, optimization, and neural networks produced major breakthroughs in AI. Today, systems such as ChatGPT and other large-scale models are primarily based on neural networks, demonstrating how far the field has advanced since its beginnings in the 1940s. We often hear people talk about machine learning, ML, and deep learning, DL. But what exactly is the difference? Machine learning, ML, is a branch of artificial intelligence, AI, that enables computer systems to learn and improve from data without being explicitly programmed. Instead of following fixed rules, ML algorithms detect patterns and relationships in data to make predictions, classifications, or decisions. Deep learning, DL, is a specialized subfield of ML that uses artificial neural networks with many layers, hence deep. These layered networks can automatically learn complex features and representations, making them especially powerful for tasks such as image recognition, natural language processing, and speech recognition. Deep learning models often outperform traditional ML approaches when dealing with large and complex datasets. Machine learning is commonly divided into three main paradigms: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, the model learns from a training dataset that includes labeled examples. For instance, given shapes labeled as triangles, circles, rectangles, or hexagons, the algorithm learns to classify new inputs correctly. However, this approach is not suitable when learning must come from interaction rather than fixed labels. In reinforcement learning, RL, instead of labels, an agent learns through interaction with an environment. It receives rewards for actions that lead to good outcomes and penalties for poor choices. Over time, the agent improves its strategy, much like how animals, or babies, learn through trial and error. Interestingly, RL is sometimes considered a form of unsupervised learning since it does not rely on explicit labels. In unsupervised learning, the model is given unlabeled data and must discover hidden patterns, structures, or groupings within it. Unlike supervised learning, no correct answers are provided. For example, the algorithm may cluster data points into groups based solely on their similarities. We next discuss what generative AI, agentic AI, and large language model LLM are. Generative AI and agentic AI represent two distinct approaches to artificial intelligence. Generative AI is focused on creating new content, such as text, images, audio, or code, based on patterns it has learned from data. Examples include chatbots, image generators, and music composers. These systems are fundamentally reactive. They wait for a user's prompt and then produce an output in response. For instance, when you ask ChatGPT to explain a concept or DAL-E to generate an image, they respond only after receiving your request. Agentic AI, on the other hand, is designed for autonomous action and decision-making in pursuit of specific goals. Unlike generative AI, it is proactive. It doesn't just generate information, it acts in the world to accomplish tasks. An agentic system may start with an initial instruction, such as book me a flight to Tokyo next weekend, and then take a series of steps on its own, searching for flights, comparing options, booking a ticket, and even updating your calendar. In short, generative AI is reactive, responds to prompts. Example, ChatGPT writing an essay. Notably, deepfakes are a product of generative AI, specifically techniques in generative models such as generative adversarial networks, GANs, diffusion models, or autoencoders. In this case, a generative AI model learns patterns from large datasets of images, videos, or audio. It then uses that knowledge to synthesize new, highly realistic content, making a person appear to say or do something they never actually did. Agentic AI is proactive, pursues goals through actions. Example, an AI assistant that books travel, manages schedules, or coordinates with other systems. Despite their differences, both approaches share a common foundation: large language models, LLMs, which serve as the backbone for today's advanced chatbots and intelligent systems. Large language models, LLMs, are advanced advanced AI systems built on deep learning architectures and trained on massive volumes of text data. Their purpose is to understand, generate, and engage with human language in ways that closely resemble natural communication. Over time, LLMs have grown more powerful and versatile, supporting a wide range of applications, from everyday writing assistants to complex tasks such as data annotation, knowledge discovery, and even the simulation of human thought processes. Lastly, let's explain what an AI transformer is. A transformer is a type of deep learning model best known for its ability to handle sequential data, such as text. It is an architecture based on the multi-head attention mechanism, in which text is converted to numerical representations called tokens, and each token is converted into a vector via lookup from a word embedding table. It serves as the foundation for many advanced AI systems, including large language models, LLMs. The key innovation of transformers is the self-attention mechanism, which allows the model to recognize and capture relationships between different parts of an input sequence. This enables it to understand context and meaning with remarkable accuracy. Transformers now power a wide range of AI applications, from natural language processing to image generation and beyond. That's it for today's video. We've covered the basics and essentials of modern AI. If you enjoyed this, don't forget to give it a like. Thanks for hanging out with us, and we'll catch you in the next one. Bye.